Welcome to day 21. Today, we're talking about one of the most reliable and widely used algorithms in machine learning, the random forest.
But first, a question. Why is it risky to rely on a single expert? Well, in machine learning, a single decision tree is kind of like that one expert. It can get so obsessed with the details of the data it's trained on that it ends up just memorizing it. It learns the noise, not the actual pattern. We call this overfitting, and it's a huge problem.
So what's the solution? Well, instead of one expert, you build a committee. A single tree might be fast, but it's fragile. A random forest, which is a team of trees, is much more robust and accurate. By the end of this, you'll understand exactly how combining many simple models creates one that's incredibly powerful.
Okay, let's build the core intuition. The genius of a random forest isn't really about complicated math. It's about a simple idea we all know, the wisdom of crowds. A group of varied, independent thinkers will almost always beat a single genius.
Think about it this way. If you need to make a big decision, like what to study, you don't just ask one person, right? You'd ask teachers, family, maybe some professionals in the field. Each person gives you a different perspective based on their own experience. Then, you'd probably go with the advice you heard most often. That's it. That's a random forest. Each one of those people is a simple decision tree, and the majority vote leads to a much better decision.
And this whole strategy of combining models has a formal name, Ensemble learning. It's built on the principle that a team of models will almost always be more accurate than any single model working alone. A random forest is a perfect example of this in action.
So this brings us right back to the original problem, overfitting. A single decision tree, if you let it, will grow wild. It will find tiny, meaningless patterns in the training data and build its logic around them. It becomes a perfect student of the past, but completely fails when it sees new data from the future. It's just too specialized.
So how do we actually build this forest of experts? The name itself gives us a huge clue. The secret is randomness. We use two key ingredients of randomness to make sure our trees are diverse and don't all make the same mistakes.
The first ingredient is called bagging, which is short for bootstrap aggregating. The idea here is that we don't give every tree the exact same textbook to study from. Instead, each tree gets a slightly different, random sample of the data. And the key here is that we sample with replacement.
So what does with replacement actually mean? Take a look here. Our original dataset has 6 examples. Now look at the data for tree 1. It also has 6 examples, but some are missing and some are repeated. For instance, example #3 is gone, but example #4 shows up twice. By giving each tree a slightly different version of the truth, we force them to learn slightly different patterns. This diversity is what makes the whole committee strong.
Our second ingredient of randomness is called attribute sampling. This one's pretty clever. When a tree is deciding how to split the data, we don't let it see all the possible features. We only show it a random subset. This stops one super powerful feature from dominating the decisions of every single tree in the forest, which again forces more variety.
Okay, so we've built this diverse forest. Now how does it make a prediction? It's just a simple vote. You take your new data point and show it to every single tree. Each tree makes its own independent prediction. Then you just count up the votes. For a classification problem, the majority opinion wins. For a regression problem, you just take the average. That's it.
Now, all this randomness leads to a really special property, which was pointed out by the algorithm's creator, Leo Breeman. He stated that random forests don't overfit as you add more trees. This is huge. For most algorithms, making them more complex is a recipe for overfitting. But with random forests, adding more trees just makes the predictions more stable.
And you can see that effect right here. As you add more trees, from 10 to 50 to 200, the error rate goes down. But then, it just plateaus. It stops getting better. But crucially, it doesn't get worse. You aren't punished for adding more trees. The collective wisdom of the crowd smooths out the errors.
So, this all sounds great in theory, but where do people actually use random forests in the real world?
Honestly, pretty much everywhere. It's considered a true workhorse algorithm. Banks use it for credit scoring and fraud detection. E-commerce sites use it to power their recommendation engines, and businesses use it to predict which customers might be about to leave. It's just that versatile.
And a big reason practitioners love it is because it's so practical. It can handle datasets with missing values without breaking a sweat. And, maybe best of all, it can tell you which of your features were the most important for making its predictions. That's not just a prediction, that's an insight.
Okay, let's wrap this up and get to the one key takeaway.
If there's one thing to remember, it's this.
A team of diverse, decorrelated experts is stronger than any single brilliant specialist. By forcing hundreds of simple trees to be different from one another, we create a final model that's both accurate and incredibly hard to fool. And that is the simple, powerful idea behind the random forest.